Hello, welcome to today's quarantine class. That's what I'm officially calling our little sessions, our quarantine classes. Good morning. So I have been posting some stuff for you to keep track of. I posted a video of a section, so we wouldn't have to meet as often live. I don't know, just giving you some options here. Maybe we can. I don't know if you like these live meetings or if you'd rather just me upload videos on your own. You let me know. But maybe we can do some meetings. Sometimes I'll record them and do them in our own time because I know things are funny and we're all adjusting to our different quarantine lives. And I'm not being too I don't know, too strict about things right now because I know we're all just going with the flow of things. All right, so I do want to remind you that we do have a test and it is posted and it's due on Tuesday. So we have almost another week, right? So we're on Thursday. You have until this upcoming Tuesday to turn it in, and you have until end of day. You have instructions on your test on how to do it, so you can scan it and email it. You can download a scanning app and send a scan that way, or you can take a pictures and upload those pictures of your complete exam. If you don't have access to a printer, that's okay. Just make it a point to write down your question and your work so I know what I'm grading, and please be me if you're going to do that. All right, so let's go ahead and continue with the section. I told you to look at it on Tuesday and I added another section along with it, but as I was making a recording for it, I was like, this section needs to be something we do together because it's very lengthy. And also it covers an important topic that you'll see in statistics that never goes away. So if you can understand it, that's my goal. If you understand how it works, that's all I care for. It has a pretty lengthy calculation. So if the calculation throws you off, I won't be too critical on that. And I'll never ask you to calculate a standard deviation here, but you will so in your next class. And the reason I won't do it now is because in your next class, you will be using technology. You'll be using one of three things. You'll be using either a calculator, which is what I always go to, but I'm not teaching stats this semester. You can also use StatCrunch, which is an application that costs about 15 bucks. And it calculates these things for you. You just have to learn how to work through it. And the third option is Excel. So Excel, you have it through your school. If you haven't done so, you have the whole Microsoft package available through Crafton. So if you want to use Word instead of Google Drive, that's fine. And I encourage it. It's free from the school. Take advantage of it. And one of the package comes with Excel. You can also do a lot of stats calculation in Excel, and it's really nice. So you can graph, you can find all these pieces of it, and you can do these calculations that you use a calculator with, but you use Excel. And that's great because Excel, it's something that most people have access to. So I won't force you to learn it I won't force you to calculate it, but I do want you to understand how it works. All right. If there are any questions, let's go ahead and start with our section for today. 2.4. All right, let's go ahead and begin. Let me share my screen, and I'm going to mute all of you just so we don't hear you like making those noises with your sheet or their calculator. I mean, for the calculator or your laptop, I'm going to mute all of you. If you have a question at any time, just unmute yourself and ask your question. Don't use the raise the hand app portion because I'm sharing my screen, so I don't have access to the Zoom screen. So just unmute yourself and ask the question. All right, let me go ahead and share my screen. Okay, so you have access to these slides. I sent them over the weekend. I sent them to you, or maybe Monday. Let me go ahead and get to my notes. These are notes from the publisher, and I really like them because it shows every single step that you're going to be working with, and it highlights what's going on. All right, before we move forward, I want to give you a sneak peek and remind you of some values we learned. So recall, before starting section 2.4, recall the mean. Now that just means the average, and I feel like average is a more common term that we're used to, but we are going to use mean, and mean is the average of your data. So you're going to add all of your data values, add all data values, and you're going to divide it by the number of entries. Right, that's our mean. Now, along with the mean, you have to remember your notation. For mean, the notation we often use are a meal, and that is your population mean, so that's everybody. And we also have X bar, and that is our sample mean. So I know we often get caught up with the notation. Don't let that throw you off. Like, burn it into your brain, so when you go into next semester, you're a pro. And another thing I want to remind you is, well, not really remind you, but kind of get you to the idea of, we're going to start working with this bell-shaped curve. And we kind of have a brief introduction to this, and we talked about skewness, how there can be a tail that's longer, either to the left or to the right, and that tells the skewness, and that affects where our mean, our mode, and our median fall. But we're going to use the bell-shaped curve, and it's pretty even. What makes it special is that it's symmetric, so that our right-hand side is the same as our left-hand side. It is symmetric, and it's a very important feature in a graph that we'll see for the remainder of our course, along with your next course. Okay, let's continue with 2.4. For 2.4, our objectives are how to find the range of a data set, how to find the variance and standard deviation, and these are where we'll spend most of our time, of a population and a sample, how to use the empirical rule and Chebyshev's theorem to interpret standard deviation, how to approximate sample standard deviation for group data, and how to use coefficients of variation to compare variation in different data sets. So again, as we move forward for the variance and standard deviation, I want you to see how it applies and how we read the information from it, but don't worry so much about calculating it, because you're going to be using some technology to do so in your next class. Okay, range. Slide 5, range. The difference between the maximum and the minimum data entries is in the set. The data must be quantitative. So your range is just subtraction. We're subtracting your biggest number minus your smallest number, and that's our range. So we have an example. 2 corporations each hired 10 graduates. Starting salaries for each graduate are shown. Find the range of the starting salaries for corporation A. All right, so we have, let's read our information. We have starting salaries for corporation A. Cool. Well, that's all it wants, right? So you have to take a moment to look at each number and say, okay, which ones are largest and which one is our smallest, right? We have our solution in our next slide. Ordering the data helps find the largest and the least and greatest salaries. So we see that our smallest number is 37 and our largest number is 47. So to calculate the range, we just have to subtract the largest minus the smallest. So 47 minus 37, and this is our answer. That's our range. The range, and whenever we work with a word question, you have to answer with the word answer. And that's something we have to get used to for the next class. So always give an answer and as a sentence. The range of starting salaries for corporation A is 10, or it's referring in thousands, so 10,000. Next slide, variation. Both data sets in the last example have a mean of 41.5 and a median of 41 and a mode of 41. And yet these two sets differ significantly. It might not seem like much. Remember, these are in thousands. So we have 41,500, 41,000, and 41,000. 500 is a pretty big number, right? The difference is that the entries in the second set have a greater variation. As you see in the figures on the next slide, the starting salaries of Corporation B are more spread out than those in Corporation A. So let's take a look at this. These two figures are very different. Do you see how here they're more closely tied together? See how here they're more spread apart? That's important to recognize in your data, because if your numbers are too far apart, you're going to know that there's going to be a large variation, and it lets you know how much each data entry would vary. Here they're closer, so they have less variability. They're more closer to each other than different. And that leads us to the main concept of this section. So we have deviation, variance, and standard deviation. Your deviation is the difference between data entry X and the mean of the data entry. Remember, difference means subtraction. So we're going to be subtracting the data entry and the mean. The population data set, your deviation would be X minus mu. And for your sample data set, your deviation would be X minus X bar. They mean the same calculation, but we have to be careful with our notation. One's for population, one is for a sample. All right, the next slide I show you looks pretty scary, but don't let that intimidate you. We use a lot of shorthand in math, and that's kind of why we've been doing all these calculations in our course, to kind of help us to be able to read that math without being so lost. Boom. Okay, so we have two formulas. You have your population variance and your population standard deviation. So they're pretty much the same. What makes it different, for the standard deviation, you have to take the square root of your answer. That square root is what makes it a standard deviation, and the standard deviation is a very powerful tool for statistics. So all we're doing, let me talk about variance first. All we're doing is we're taking each data set and we're going to subtract. We're going to subtract the average to each one. So it's helpful if you set up like a chart where each data entry gets subtracted by your average. Once you do that, oh, I lost my slide. Once we do that, we want to square each one. So let me go back to that. There we go. I think we're in slide 10. Here we go. So like I said, we're going to subtract the mean to each one. And after we do that, we're going to square our answer. So we're going to square each answer after that. And lastly, we're going to add each entry. That's kind of the larger calculation for your standard deviation. At the very, very end, we're going to divide by the number of data entries. So let's go ahead and do an example, because I'm sure me pointing out a formula isn't helping. Deviation, variance, and standard deviation. Observations about standard deviation. The standard deviation measures the variation of data set about the mean and has the same units of measure as the data set. The standard deviation is always greater or equal to 0. When the standard deviation equals 0, the data has no variation at all, and all entries have the same value. So you could get 0. That's possible. As entries get further from the mean, that is more spread out, the value of sigma increases. So this letter is called sigma. And that's your standard deviation. So here are your steps to finding the standard deviation. And you have it in words and in symbols. First, you want to find the mean of the population data set. So that's just your average, right? I write it here in parentheses. That's your average, our mean. Find the variation of each entry. So for each entry, you're going to subtract the mean. You want to square each answer. And lastly, you want to add all of your data entries. I'm sorry, all of your squared entries. And that's called the sum of squares. 5, you want to divide by the number of data entries by n. And lastly, take the square root of your answer. Let's go ahead and do an example. Find the population variance and standard deviation of the starting salaries for corporation A listed in the first example. So it kind of gives you a piece to find the mean. It tells you that there are 10 data entries. If you add them all up, it's 415. So 415 divided by 10, I have 41.5. That's our mean, right? So we have to remember our mean is 41.5. Okay, let's go ahead and calculate the standard deviation. So let me jump back to our slide. We did step 1, we have our mean. Step 2, you want to subtract each data by our mean. So it's helpful if you have a box. So what they did for you is they put each data entry in a box for you. And we're going to subtract. All these numbers are the same ones we have here, right? And all we're adding is a subtraction. And what are we subtracting to? What are we subtracting from? We're subtracting from the mean. So we have to calculate that subtraction. And we see we have 41 minus 41.5. Next one is 38. 38 minus 41.5. Next data entry 39. So 31 minus 41.5. And we're going to do that for each one. I know it's very tedious. That's the work for it. All right, what's next in our step? We did step 2. Step 3, you want to square each answer. So each one of our answers, we want to take the time and raise it to the second power. That would be our step 3. So we go on to slide 17. We're going to take each one of our answers. We see our work here for each one of our answers, and we're going to square it, raise it to the second power. And we have our answer here. 0.25. If we square 0.5, negative 3.5 is 12.5. Negative 2.5 squared is 6.25. And we have all these answers. We're going to square them. That's our answers for our square. Now we were asked to then add them. So we have our sigma here, our sum of all of our squares. That's our sum of squares. So if I add all of them up, they add up to 88.5. You did the whole top part, just about. Last piece, let's go back to our formula. So here is our formula. We did this part here, that I'm highlighting in yellow. We did this, we squared them and we added them up. We got 88.5. Now we have to divide up by the number of entries, which was 10, and this is our answer. 89.9, this is our variance. Lastly, to get our population standard deviation, we take the square root of that. Now here it sets you up with the same work, but you can take your answer and square that and do the square root of that. So once you take the square root, you get something close to 3.0. So where's our answer? The population variance is about 8.9 and the population standard deviation is about 3. And it's all referring to thousands, so it's about 8.9 thousand and 30,000. Well, that was a lot. Let's take a moment to go over these steps one more time. So first, we're going to find the mean. That's step 1. Step 2 is we're going to subtract each data entry by the mean. Step 3, after we subtract it, we're going to square them and add them. Then we're going to divide by the number of data entries, and that will give us our variance. To find the standard deviation, we take the square root of that. So we have the mean that we calculated. Now we're going to take each data entry and subtract the mean. So we're subtracting all of them by our 41.5, which was our average. That's our average, and we're subtracting that to each data entry. Then we want to square our answers. So do you see your answers here that I'm highlighting in yellow? We're going to take each one of our answers and we're going to square them, which is what we did in the next slide. After you square each one, you want to add them. And that gives you your SSX in the bottom, your sum of squares. Okay, that's the hardest population. Now you can refer back to your formula. So for your variance, you're going to take your sum that resulted in 88.5 and divide it by the number of data entries, which was 8.9. To find the population standard deviation, we're going to take the square root of our answer, which is about 3. All right, so let's sum up here. So what we did was we found the variance and standard deviation of the population. We're going to do a couple more examples that deal with standard deviation and variance. We're going to next work with a sample, variance and standard deviation, and then we're going to work with group data. What's different from the problem we did before? Well, we had each data entry separately, so that's more like your raw data. Let's continue with this slide 19, deviation, variance, and standard deviation. And now we're going to be working with a sample. Now, what's the main difference? Take a moment to look at your denominator. That gives you a totally different number than what you had before. So it's the same calculation, but once you get to dividing, you don't want to divide by the number of data entries, you want to divide by the number of data entries minus 1. And that's the difference between a sample and a population. Also known as your notation. It's different, right? Remember, for a population, we used a sigma, a lowercase sigma. That looks something like that. Now for a sample, we're using an S. Okay, let's continue with an example. We have the same steps at the end, it's just slightly different. So let's take a look at our steps. Our first step, we're gonna find the mean, just like before. 2, subtract each data entry, subtract the mean. 3, we want to square our answer. And 4, we want to add up our sum of squares. And then we want to use that into our formula. We did all the work in the previous slide, which was this numerator. And for 6, your standard deviation, you take the square root of your answer. So let's take an example. Let's take a look at an example. In a study found of high school football players that suffered concussions, researchers placed the players in 2 groups. Players that recovered from their concussions in 14 days or less were placed in group 1. Those that took more than 14 days were placed in group 2. The recovery times and days for group 1 are listed below. Find the sample variance and standard deviation of the recovery times. All right, so here is all of the data we got. Now first we want to start off by finding the mean, our X bar. Take a look at the next slide. So here it kind of did it for us, but let's calculate ourselves. Let's do all that work it's not showing. So let's take the one to add all of them. So we have 4 plus 7 plus 6 plus 7 plus 9 plus 5 plus 8 plus 10 plus 9 plus 8 plus 7 and plus 10. And we said we had 10 data entries. So when I add them all up, I got 90. And we said we have 10 data entries. Do we? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, we have 12 data entries. So we're going to divide it by 12. 90 divided by 12, we get 7.5. So that's our average. Next, it's going to show us our answer after we subtract each data entry. So we found the sum, which is 90, and we divide it by those 12 entries. Now I have to subtract your number minus your standard deviation. So for that first one, it doesn't show the work, but I know it was 4 minus 7.5. And 4 minus 7.5, we get negative 3.5. So that works out, right? Next, I'm going to do 7 minus 7.5. I get negative 0.5. One more, 6 minus 7.5. And I just want to show that work that it's not showing you in your box. But you're doing your calculator for this, do a subtraction. Now next you want to square each answer. So you want to take each one of your answers and you want to raise it to that second power. And we get this answer here. Okay, so we have our squares in this box right here. Now we want to make sure we add them. That's all of our work for our numerator. Now let's take a moment to look back into our formula in the next slide. So for this answer, we saw that n is 12, meaning we have 12 data entries. The sum of all your entries is 90. That's what sigma x means. And the mean, x bar, is 90 divided by 12, which is 7.5. To calculate s squared and s, note that n minus 1 equals 12 minus 1, which is 11. So that's this number right here. It's 12 minus 1, we get 11. And that's our denominator. Okay, when we added all our sum of squares, remember from below, our sum of squares is 39. So we're going to take 39 divided by 11, we get 3.5, and that is our variance. Lastly, to get our standard deviation, you can just take the square root of that. Square root of 3.5, and you get something close to 1.9. When I calculate into my calculator, I get 1.8708. And right here, we're rounding. Okay, so we see how they got that. Now, the sample standard deviation is that one thing that we will see throughout the course of statistics. So make sure you don't have to make sure you know how to calculate, because as you move forward, it's usually going to be given. But by the end of this PowerPoint, hopefully you understand what it means. Okay, one more. So we can skip this one. It's just telling you how to use technology. And it's pretty cool. So let me just jump to the next slide. So if you have a calculator, which is what I like to use, we're gonna put their data into our list. And once we have a list, we tell it to spit out this information, and it tells us everything. It tells us our mean, our x bar, the sum of everything, everything squared, our sample standard deviation, our population standard deviation, the sum of everything, and it gives us more information too if we scroll down. Minitab, which is what some instructors use, they also call it StatCrunch. It's a way to work with things that give you more information. What you'll probably work with is Excel. And for Excel, we enter all of our data in a row. So you enter it, press enter, and then there's one command that will tell you all of the summary. The pieces that we'll be worried about or want to know are the standard deviation and the mean. It will be nice to know your range, maybe your minimum and maximum numbers, your median and your mode. But a lot of the other stuff we do, like kurtosis and skewness, we don't really get to in the stat course that you learn here. Next, interpreting standard deviation. The standard deviation is a measure of typical amount of entry deviates from the mean. The more entries are spread out, the greater the standard deviation. And that's key. The more the entries are spread out, the greater the standard deviation is. So if you have a bigger standard deviation, that means each data entry, they're more different from one another than closer. And if ever you're unsure, it's always helpful to think about math as food or as money, and that usually clears things out. So if you think about money, it means that each person has different amounts compared to the next person, if you lay them in order from smallest to largest. If you have a small standard deviation, that means they all make about the same amount of money. Whether it be a lot or a little, doesn't matter. It means they make about the same. Now here you see a standard deviation of 0 for this first graph. And we see that the data entries are all the same figure. They're all the same amount. So there is no spread at all, meaning they don't vary at all. They're all the same number. So that's when you would see a standard deviation of 0. Now, as it gets a little bit bigger, like we see in the next slide here, it's a little bit bigger. And we see these data entries, they're pretty close to each other, right? Notice that your smallest amount is 3, your biggest amount is about 7.5 or 7. And we see that, well, 4 isn't so much far apart. So I guess that's not so far. And we have a mean of 5. Okay. So the data entries are pretty far apart, but not so bad. Now let's take a look at our next graph. Without even looking at our standard deviation, look at your graph. What is the smallest number? What is the largest number that you have? Well, those are more far apart, especially if we think about them as thousands. That's almost 6,000 apart from one another. Now let's take a look at our standard deviation. You see how it's bigger? So there's a bigger spread between our data entries. And that's all this funky figure means. It's the spread, how far apart numbers are from one another. So if you're just thinking, man, this is so weird, what is this? It's just the spread. Look at this second bullet point. The more the entries are spread out, the greater the standard deviation. Now we have two notations for standard deviation, and I just want to highlight them again. So the standard deviation for a population is a sigma. And the sample standard deviation, the sample, is a S, letter S. So don't let use the notations fool you, okay? So what have we learned so far? We learned standard deviation. We have S, standard deviation, and S. And we also have the means, right? Don't forget that your population mean is a mu, and your sample mean is an X bar. All right, moving on to our next slide, 28. Without calculating, estimate the population standard deviation of each data. Okay, so we can kind of see what things are. So here we have 8 entries, and we see we only have 1 entry for all of them. So we know our standard deviation would be 0. Okay, here we have a mean of 4, which is here. And our smallest and biggest number go from 4 to 5 and 4 to 3. There only seems to be 1 apart. So I would guess it's something close to 1. Now let's take a look at our mean. Our mean is 4. So how far apart are these numbers from 4 to left and right? So we have from 4 to 1 and from 4 to 7. Maybe a standard deviation is 3. And we see, yeah, that's our previous slide, right? Isn't that our previous slide? No, it's something different. Okay, now we're gonna walk through how the standard deviation what the answer is. But here is our guesses. And our guesses come from how far apart are they from the middle? because the middle tells you so much. Okay, let's go on to our next slide. So for the first one, each of the 8 entries, 4 is 4. So the deviation of each entry is 0. So our standard deviation is 0. Okay, that wasn't so bad because if they're all the same entry, there's no variation, that's 0. We saw that on the example, we got that one. The next two is where I'm worried about our guess. Okay, each of the 8 entries has a deviation of 1 more, plus 1 more, and minus 1 more from our mean of 4. So the population standard deviation would be 1. By calculating, you see that your sigma is equal to 1. 3. Each of the 8 entries has a deviation of plus 1 or plus or minus 1 or plus or minus 3. So the population standard deviation would be about 2. By calculating, you can see that it is greater than 2, so about 2.2. Not far off, right? So our third one was 2. We guessed 3. I think that's a pretty good guess. All right, any questions so far? All right, let's continue with slide 32. Interpreting standard deviation, empirical rule. All right, so this is where the students get it well, but it takes a minute. So make sure you ask questions if you have any. Now this is really key because it kind of gives us a sneak peek of proportions and a common topic that we'll see in future chapters. All right, let's read our text. For data with a symmetric bell-shaped distribution, the standard deviation has the following characteristics. One of them is about 68% of the data lie within one standard deviation of the mean. Second, about 95% of the data lie within 2 standard deviations of the mean. And third, about 97% of the data entries lie within 3 standard deviations of the mean. So without looking at the next image, let's make a picture of what we think this means. So if we have a bell-shaped curve, all right, and we have this mean, this average, and if it's symmetric, our mean is right down the middle. Okay, this is saying that 68% lie within 1 standard deviation. So if it's within 1 standard deviation, so it would be 1 standard deviation to the right and 1 standard deviation to the left. So with that cutoff point, that means that 68% of all our information lie within that range of our bell-shaped curve. That's all that's saying. So now we're going to take a picture that puts all of this together. Take a moment to see what we have. We have this beautiful bell-shaped curve. That's super important. There has to be a bell-shaped curve. Next, we have listed our mean. Our mean is right down the middle. We have X bar, but we can use mu if we have a population. Now, look at these colors that you have in your graph. We see that within 1 standard deviation, you have 68% of your data. So 68% of your data fall here. Now, what's special about that? It's 1 standard deviation away. So 1 standard deviation away from your mean to the right and 1 standard deviation away from your mean to the left. Let's talk about a bit more. So we also have that within 95%, 2 standard deviations away from the mean. Okay, so that means that from our mean, if we go 2 standard deviations, 1, 2, 1, 2, this will cover 95% of all of our data. So from 2 standard deviations, we have 95% of our information. And lastly, we have 3 standard deviations. 99.7% of your data is within 3 standard deviations. So from your mean from the middle, we have 1, 2, 3 standard deviations. 1, 2, 3. This means that this covers 99.7% of your data. Just about your whole curve. So everything should be about within 3 standard deviations. And you have a bit more in your tails, right? A bit more going on. 0.03 on each side. Well, 0.03 the sum of both sides. Our entire bell-shaped curve adds up to 1. So the sum of all of the curve adds up to 100%. Or if we change it to decimal form, we move the decimal over to the left too, it'd be 1.0. So this means that our whole curve adds up to 100% or 1. And this is the probability or percent of things happening. And this is the role that the standard deviations play. From your mean, how far apart is it? And that tells you a percent that applies to your information. Now, keeping this in mind and keeping this distribution, we're going to work with some problems. Please note this rule right here. Within 1 standard deviation, we have 68%. Within 2, 95. Within 3, 99.7. Okay, let's do an example. In a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States, ages 20 to 29, was 64.2 inches, with a standard deviation of 2.9 inches. Estimate the percent of women whose heights are between 58.4 and 64.2. Well, that's a lot of information. Let's take a moment to read again and highlight some important pieces. All right, in a survey conducted by National Center for Health Statistics, the sample mean, okay, we have a mean, of women of the United States, ages 2029, was 64.2. All right, that's our mean. Let's write that down. With a sample standard deviation of 2.9, okay, sample standard deviation is 2.9. Estimate the percent of women whose heights are 58.4 and 64.2. I kind of don't know what to do with that. But maybe I can use the empirical rule. My empirical rule says that if I have a bell-shaped curve, my mean is down the middle, which is 64.2. And I can add and subtract the number of standard deviations to work from there. Okay, so I want to work between 64.2. Hey, that's my mean. Between that and 58.4. Okay, so I have to go down a bit more. So I can go down 1 standard deviation, 2 standard deviations, and 3 standard deviations. Okay, take a moment to subtract. Maybe we can find that number. So let's take 64.2 and let's subtract 1 standard deviation. If we subtract 1 standard deviation, we'll be subtracting 2.9. So 64.2 minus 2.9, we use our calculator. We get 61.3. Is that the number we want to get to? No. So let's subtract another standard deviation. Let's subtract 2. So 64.2 minus 2 times 2.9. Or we can just subtract 2.9 from 61.3. Okay, that gets us 58.4. So that's within 2 standard deviations. So we want to find the percent that falls between 2 standard deviations and our mean. That's the number of women who fall between those 2 numbers. Let's take a moment to look back. From our mean to 2 standard deviations away, how much does that add up to? Now it takes a moment to split up all of our chunks, right? So we have to add our percents. We have 34% plus 13.5%. That's going to tell us the percent that fall underneath that amount. The next slide shows us that. So we're here. Let's move on to the next slide, 35. And we see our answer in blue, right? That we just calculated. We see it in blue. Let's read our bullet points. The distribution of women's height is shown. Because the distribution is bell-shaped, you can use the empirical rule. The mean height is 64.2 inches. So we see that as a mean. And we're subtracting 1 standard deviation. So minus 1 standard deviation, minus 2 standard deviations, and that got us at the point we want to get to, 58.4. Now we have to add these percentages. And if you're ever unsure, you look back at your empirical rule. So make sure you have this picture handy. It'd be helpful if you just start getting familiar with it. It's nice because it splits it up. So for example, it tells you that 1 standard deviation is 68%, and it splits up those 68% into 2 halves. 1 half to the right of the mean and 1 half to the left of the mean. So 68 divided by 2, we have 34 and 34. And that's really helpful, really nice. Moving forward, when you subtract 2 standard deviations from the mean, you get 58.4. So it's showing us the work we did here. Back to slide 36. Because 58.4 is 2 standard deviations below the mean height, the percent of the heights between 58.4 and 64.2 inches is about, we add our percentages. 13.59 plus 34.13, we got about 47.2. So about 47.72 of the women are between 50 and 64. Next, we have Chebyshev's theorem. And it's also fun to say. The proportion of any data set lying between k standard deviations of the mean is at least. So here we have a way to calculate the percent. So it tells you the percent of your data entry within so many standard deviations. So here it tells you if you choose k to be 2, in a data set at least 1 minus 1 over 2 squared gets you 3 over 4. You punch into your calculator, you get 0.75 to 75%. So you can say about 75% of your data lie between 2 standard deviations. Or if you enter 3, you get 8 over 9, which is 88.9. So 89% of the data lie within 3 standard deviations of the mean. All right, so let's do an example. And we use Chebyshev's theorem. The age distribution of Georgia and Iowa are shown in the histograms. Apply Chebyshev's theorem to the data for Georgia using k equals 2. What can you conclude? Is an age of 100 unusual for Georgia resident? Explain. Okay, so let's take a look at this. So we have a mean. Let's look at each graph separately. For the first one, we have a mean of 37.3. So somewhere about here is our mean, right? We have a mean, a meal. And our standard deviation is 22.3. And we see that our lowest number, of course, would be something close to 0. And our highest is something close to maybe 90 or 85. Okay. And we see there's more younger people than there's older people. Okay, let's take a look at Iowa. We have a mean of 39, so it's a bit more, right? So somewhere right here we have our mean. And we have a lot of younger people, a lot of older people, but we have a higher mean. Let's take a moment to look at them side by side. And we see that Iowa, there's less people, right? There's more people in Georgia. Okay, so let's go ahead and continue using Chebyshev's formula. Oh, did I skip a question? Okay, so you want to know The age distributions from Georgia and Iowa are shown in the histograms. Apply Chebyshev theorem to data for Georgia using k equals 2. What you conclude is an age for 100 unusual for Georgia resident? Explain. All right, so what is our Chebyshev's formula? It's, you can take a look at the slide back. You have 1 minus 1 over k squared. Okay, so it's being told that k is 2, so I have 1 minus 2. So that's 1 minus 1/4. You can punch it into your calculator or subtract leading fractions to get 3 over 4. It's about 75%. So 75% of your data lies between 2 standard deviations. All right, so if we do our work, we have k equal to 2. If we subtract, we get 37.3. Oh, minus 2, we get negative 7.3. And we can't use that since we can't have a negative h. And if we add 2 standard deviations, we get 81.9. So you can say that at least 75% of your population of Georgia is between 0 and 81.9 years old. Also, the age of 100 lies more than 2 standard deviations from the mean. So this age is unusual, which is about the same conclusion we got from Chebyshev's theorem, right? Standard deviation for group data. All right, this one is challenging. I want you to see it, but again, I will not ask you to apply it. I won't ask you to calculate it, I mean. So we have our formulas for standard deviation. We call that your sample standard deviation for frequency distribution. We have a slightly different formula. So our formula will be the same, but we're adding this times f to it. When the frequency distribution has classes, we estimate the sample mean and the standard deviation by using the midpoint of each class. So this is when we have group data. So say we have these 50 entries and we put them into a chart. We put them into a chart where we have the number between 0, 1, 2, 3, 4, 5, and 6. So we're categorizing all of our data. Okay, so we want to take a moment to find the mean first. To find the mean, we have to multiply and divide by the number of data entries. So 0 times 10, 1 times 19, 2 times 7, and we add the number, we add them up. And this is all the work we need to do to find the mean. And why do we do it this way? We do it this way because we group this data. When you group data, you work with things slightly differently. Okay, now I want to continue to find the standard deviation. Well, it's pretty similar, but again, slightly different. So you want to start off by subtracting your number minus your mean. Okay, so we have the number for each one. We have 0, 1, 2, 3. We're going to subtract each one from the mean. And then we're going to go ahead and square each answer. And this is where we find the sum. Now, what we have to do differently is after we find the square, you want to multiply it by the frequency. So multiply it by your f. And you can do it using charts. And it's kind of just repetitive work. After you multiply it by your frequency, now you can go ahead and add it. And this is the number you'll use in your formula. So you have 145.38. Remember, it's n minus 1, so we had 50 entries minus 1. That's where that 49 comes from. You take the square root, so your standard deviation is about 1.7 children. Okay, we're going to do one more example of standard deviation with group data. Now this one, what we did, take a moment to look at your x. Each one was a number. But what if we had a range like 1 through 5 and 6 through 10. How will we go about it that way? That's our next example. And again, I know it's complex. I won't ask you to calculate it. You won't have a problem in your My Math Lab where you're asked to calculate it. Just know that the standard deviation is a spread, how far the numbers are from one another. Example, using midpoints of classes. The figure shows the result of a survey with 1,000 adults. We're asked how much they spend on preparation for personal travel each year. Make a frequency distribution for the data. Use the table to estimate the sample mean and the sample standard deviation of the data. So here they tell you, let's look at what they tell us. They give us a range. So between 100 to 199, we have 230, 200 to 299, we have 210, and it keeps moving around the circle, right? 300 to 399 is 50, 40 to 499 is 60. So let's put that into a chart. Begin a frequency distribution to organize the data. Because a class of 500 or more is open-ended, you must choose a value that represents the midpoint. All right, so here we have our classes. We have 0, 99, 100 to 199, which is what our picture gave us, right? Now we had to do a little bit of work. So you had to take the moment to find the midpoint. That's what we had to do. And now we can complete our problem like we did on the last example. Now, how did you find the midpoint? You take your numbers. So say 0, you add 99, and you divide it by 2. That gives us 49.5. For the second class, you do the same thing. You add your lower and your upper, 100 plus 199 divided by 2, you get 149.5. So this is the midpoint that you had to find. Now you go about it the same way. You multiply your x and your f, so we have to multiply these two numbers. 49.5 and 380, 149.5 and 230. We multiply them and we add them up. And we did this to find our mean, so that we have a mean of 192. This is how we find the average of group data. Now we have to continue forward and find our standard deviation. So if you use a chart, it helps you keep track of your calculations. Now we're going to take our midpoint, our x, and subtract it by your mean that you found. So our x are our midpoints, and our average, we just figured that out. It's 182. So we're going to subtract each one of those midpoints by 182. And that's what our next chart shows, our answer. So when we subtract, we get negative 142.5, negative 42.5, 57.5. And next, I want to go ahead and square each one of those numbers. They're big numbers. After we square them, we want to go ahead and we have our answer, and we want to go ahead and multiply it by our frequency. So how often that happened. We have our number in our previous chart, 380, and so on. So 380, 230, 210, 50, 60, 70. We take a moment to multiply them here. Ooh, those are really big numbers, and then we want to go ahead and add them to find our standard deviation. So to find our standard deviation, we want to take the square root of that and divide it by n minus 1. Remember, we had 1,000 entries, minus 1, we get 999. You find the square root of that, and we get 160.3 for your standard deviation. Now again, I won't ask you to calculate this by hand. Chances are when you go on to your next course, you might do an example in class where you do it by hand, but you'll learn how to use technology to do this. Moving forward, solution using midpoints of classes. An estimate for sample mean is 182 per year, 192 per year, and the estimate for the sample standard deviation is 160.30 per year, which is where our answer was. Next, we have coefficient variation. Coefficient variation, or CV, describes the standard deviation of a data set as a percent of the mean. So all this is we're going to take our standard deviation and divide it by our mean and multiply by 100%. We have these here. So let's look at an example. Comparing variation in different states. The table shows the population heights and weights in pounds of members of a basketball team. Find the coefficient variation for the heights and the weights, then compare the results. Okay, so we have to do this separately. We have to find first, for the heights, we want to find the mean. Then once we find the mean standard deviation, and once we do that again, we want to do that with the weights to find the mean and the standard deviation. And then once we do, we can use that formula. So we can compare them. So we have, for the mean height is 72.8 with a standard deviation of 3.3. So the coefficient of variation for the height is, we punch that into our formula, we get 4.5. We can do the same thing for our weight. Now it's telling us, and I'm not making a calculator because I'm sure you're tired by now, we've been here for a while. Our mean is telling us, it's given to us, it's 187.8, and our standard deviation is 17.7. We have our formula, we plug it in, we get an answer 9.4. So we have two answers, one of 44.5 and one of 9.4. The weights of 9.4 are more variable than the heights of 4.5. Right, so it gives you which ones differ more. Variability is how far apart, how different they are. And that's it for this section. All right, so let me get back to our screen. So thank you for sticking around. I know it was lengthy, but it's an important lesson to get through. What I want you to get from here is standard deviation, which just is how far apart things are. And this far apartness comes from in relation to your mean. How far apart is it from the mean and how far apart each data is. So in summary, what we should have learned is just the general idea of a standard deviation, which is the spread of things. And the second most important thing from here should have gone is the empirical rule, because you'll see this show up again for sure. And that is how 1 standard deviation, 2 standard deviation, 3 standard deviations, what percent of your bell-shaped curve lies between those values. So I'll post this lesson on YouTube. Give me about an hour until I post it. It takes a while for Zoom to get back to me, and then a while to upload on YouTube. So those of you that couldn't join, feel free to check it out in your own time. And that's it for today. I'll open up your homework for this section. It won't be too much because I'm not going to ask you to calculate standard deviation, but just some questions that maybe ask about spread or the empirical rule, something like that I might ask for your homework. All right, well, if there aren't any questions, have a nice day. Thank you for showing up today, Abby, Cameron, Felicia, Sarah, and Victoria. Thank you so much. All right, I'll post this on YouTube. Have a nice day. Have a nice weekend. Maybe I'll see you on Tuesday. We'll have Tuesday, and then we'll do a recording for Thursday to watch on your own time. All right, have a nice day.